All right, so yesterday's lecture we finished up talking about dihydroxylation reactions, and we said that there were two different types. The first was the anti-dihydroxylation, where you get alcohols where one's a wedge, the other one's a dash. Typically you can't control the mixture, so you just get a mixture of stereoisomers. In this case, it'd be a 50-50 mixture of enantiomers. Oftentimes, what we'll see as the reagent used is MCPBA. However, often you'll also see alternates. So let me write down some alternate reagents over here. Oftentimes you'll see CH3COOH. That's peroxyacetic acid. This is the other alternate reagent that you often see in the Klein textbook. If you notice in both of these, they have these peroxy bonds right there. So either one is a useful reagent for this transformation. And like we said, in the mechanism, we form this unique molecule where we've got oxygen in a three-membered ring, and that's called an epoxide. And once you form your epoxide, you can protonate that oxygen. Water can add in to either side, really, it doesn't matter. And that will give you typically a mixture of products as a reaction mixture. You do need to show that final deprotonation step at the very end, but either way, it gives you your antidiol. And then the other option was Syn dihydroxylation. Again, this was a mechanism I didn't expect you to memorize. I just said, remember the reagents. So osmium tetroxide followed by sodium bisulfite and water gives you the Syn diol. We said in this example, it's a meso compound, so we don't need to worry about enantiomers. And then we said we could use potassium permanganate, sodium hydroxide, and run it cold. Either one of these work well. Yeah?
Is it possible to have a solution of both the anti and the syn?
So the question was, can you make a product that's both syn and anti? Mm-hmm. Not really. In general, you want to pick one or the other because you don't want to make a needlessly complicated mixture. Yeah. All right, the next reaction is kind of neat. It's similar to what we saw previously, but we're going to oxidize things even more. So I'll show you the net reaction first. Whoops. And this is called ozonolysis. And I'm even going to show these assumed hydrogens for right now, and you'll see why in a second. But when you do ozonolysis, what you need is an ozone generator that produces O3. Does anybody know what ozone is or does in our atmosphere? What does it do?
It prevents harmful UV radiation from reaching that.
Exactly. So ozone is a natural gas found in our upper atmosphere, absorbs UV light, protects us from things like skin cancer. Alternatively, when we have it at the ground level, it's actually a health hazard. You don't want to breathe in a lot of ozone, and you'll see why. So first step is react it with ozone. And then second step is to react it with something called DMS, or you can use zinc and water. You might see these used kind of interchangeably in the Klein textbook, so I show students both. What DMS stands for is dimethyl sulfide. It just means you have two methyl groups attached to a sulfur atom. So DMS is a common reducing agent. It's just a little stinky to work with. All right, in this reaction, what we essentially do is we cut this double bond and we insert oxygen atoms. So let's take a look at what that looks like, and I'm going to draw this kind of exaggerated. But you see how this, let me keep the colors the same. These oxygens were inserted where that cut is. What new functional groups have we made? It's an aldehyde, right? And I'm going to put or ketone in parentheses there. Why might we get a ketone? When would that happen?
Carbon.
Yeah, what if we swapped out these hydrogens for some sort of carbon group, right? We could still cut that, but then instead of getting an aldehyde, we'd just get a ketone out. Exact same process though. All right, it looks kind of funny to draw it this way. So oftentimes what I do is I just say, all right, this is 1, 2, 3, 4, 5, 6. So we can redraw this as a 6-carbon chain. We can say, well, this must be that aldehyde. So it looks a little prettier to unwind it like that. But either way you draw it, you're showing the correct molecule. All right, so now let's take some examples here. And I want you to help me predict what the products would be. So in this first example, we'll treat it with ozone and then zinc and water in step 2. It's important to number these as step 1 and step 2. But let's try to predict what the product would look like here. See if you can figure it out and then check with your neighbor. Who thinks they got the product or products from this reaction? Let's see a show of thumbs. Thumbs up if you got it, thumbs down if you're completely lost, sideways if you're like, maybe. All right, looks like a lot of sideways, a few thumbs downs. So let's take a look. So I'll use my dash system to say we're going to make a cut smack through this double bond, right? And when we do that, we're going to insert oxygens where that double bond used to be. So we'll have an oxygen there. And we'll have an oxygen there, right? So essentially we're going to get 2 different fragments. And this is where that cut occurred. Does that kind of make sense? What's the relationship between these 2 products? They're identical. So in this case, we would get 2 equivalents of the same ketone. So in this example, we're not getting aldehydes, we're just getting 2 ketones out, right? Does this make sense? Good thing is you don't need to know the mechanism for this. I'm not going to force that on you. You can go through the mechanism in your textbook if you'd like, but I've found that it's just kind of overwhelming as is in this chapter, so we're going to try to boil this down. All right, let's do another example. This one's going to be a little bit trickier. So this one, we've got an alkene that looks a little bit different. All right, so same idea. Let's check with our molecular scissors. We're going to cut it with that red line. What I like to do here is show the assumed hydrogens, because sometimes it gets a little confusing without showing the assumed hydrogens. So what I'll do is I'll draw those in blue. Say we know that we've got 2 hydrogens coming off that point, right? So if we think about the top half, we'd still have these 2 hydrogens. And then underneath it would be bonded to an oxygen now, right? So this would be 1/2 of the cut. And then the bottom half of the cut will look pretty similar, but it'll look like that, right? Does anybody know what this top molecule is? Formaldehyde. It's what they used to use to embalm animals and even people before a funeral or something like that. However, now it's not commonly used. Does anybody know why? causes cancer. So we kind of learned the hard way that this isn't the greatest thing to use. However, when we cut these double bonds, it's important to remember that you can make even something as simple as formaldehyde during these ozonolysis reactions. All right, let's try a harder one. And we're going to assume that we have excess of our reagents around, meaning we've got plenty of ozone. Does anybody have an idea of what might happen if we have plenty of ozone around? Could do more than one cut, right? So let's try to figure out the pieces that might result from this. So really quickly, I'll just get us kind of going here. We're going to cut this double bond, and because we've got excess, we'll cut this one. I'm a big fan of drawing in assumed hydrogens off of alkenes just because it makes our lives a lot easier, right? All right, so now let's go ahead and figure out what the pieces are. Well, we know that this piece must look a lot like that, right? Because we're going to cut off that left-hand chunk of the molecule, again, making formaldehyde. On the other side, though, we're going to have kind of this in-between chunk. It's going to look like this, and it's being cut in two spots. So really, this whole portion is this whole portion. Does that kind of make sense so far? All right, so we've got that taken care of. And then last but not least, got oxygen with the double bond there. What's this molecule called? Anybody know? Give you a hint. You use it to clean your glassware when it's really dirty. Use it to clean the IR. Not Windex. Acetone. Yeah, so we can make acetone, a super small ketone that way. All right, so this is a pretty interesting reaction. How many of you have ever gotten on your bike, maybe it was your old childhood bike, and you look at the tires and the tires look all cracked and old? Have you seen that? So the term for that is called rubber rot. It's actually this reaction taking place. So if you think about rubber, right? Rubber has a bunch of double bonds in it. We've got a trace amount of ozone in our environment. And when that ozone reaches those double bonds in your rubber, it will actually split those double bonds and cause rubber to slowly degrade over time. It's a really big problem for NASA. In fact, if you remember the Challenger explosion, one of the problems they had was an O-ring failure. And there's a lot of suspicion that ozonolysis actually decomposed that O-ring and it needed to be replaced because it had some cracking going on. So anytime you're dealing with really high precision applications, you have to worry about things like rubber rot due to ozonolysis. So real world application there. All right, next one is a fun reaction, catalytic hydrogenation. All right, and in this reaction, I'm going to actually color code things. I'm going to say, all right, we've got an alkene with two hydrogens, kind of like in the last reaction. But this time, the gas we're going to use is hydrogen gas. And oftentimes, you need a catalyst. It can be a variety of catalysts. It could be palladium. It could be platinum. Sometimes there's more exotic ones. Usually, they're absorbed into charcoal. So oftentimes you see something like palladium on carbon as an example. Why did we absorb palladium onto charcoal? Does anybody know why? Two reasons. Is palladium cheap? It's really expensive. Like $10,000 for a bottle expensive. So you don't want to use very much palladium, right? The other benefit to charcoal is it has a massive surface area, right? So if you're trying to increase the reaction rate, increasing surface area helps you out a lot. So you'll often see this either palladium or platinum. And what this does is it will add 2 hydrogen atoms across. Specifically, it'll add 2 hydrogen atoms in a Syn orientation. So you get Syn addition of hydrogens. So it's a really clever way to convert an alkene all the way to an alkane. And I'll show you the most practical example that we see in our day-to-day lives. I'm just going to make this up. What sort of functional group do we have here? So is this a carboxylic acid if that R group is a carbon? No. It's an ester, right? In fact, this is a common type. This is an oil. It's often found in things like vegetable oils, right? So vegetable oils, are they solids or liquids normally? Liquids. So like canola oil that you have at home is a liquid. What they found out in the 30s was you could do this reaction where you take hydrogen gas, palladium on carbon, and what do you think happens to these vegetable oils? Yep. Let's see, 1, 2, 3, 4, 5. Whoop, 1, 2, 3, 4, 5, 6, 7. There we go. All right. So what we've done is we've taken an unsaturated fat and we've made it a saturated fat. Are saturated fats normally solids or liquids? Okay, so this is normally a liquid. This is normally a solid. And what they found is they could convert vegetable oils from a liquid to a solid. And the question is, well, why would this ever be useful? Well, during World War II, there was a big shortage on butter, right? Because of the war effort going on. So what they found was, hey, we can just get a bunch of vegetable oil, hydrogenate it, and you make something that looks a heck of a lot like Crisco. How many of you have cooked with Crisco? So Crisco is hydrogenated vegetable oil, exactly like this. Does anybody know the downside of using something like Crisco that's a hydrogenated vegetable oil? It's terrible for you. Why? Causes heart disease. In fact, what happens during the hydrogenation process is they don't want to hydrogenate all of the alkenes because otherwise it's like a brick. It's not fun to cook with. So they partially hydrogenate it, meaning they want to hit maybe half of the double bonds, but not 100% of them. But what happens is they scramble some of the double bonds from the cis configuration, shown here, to a trans configuration. How many of you have heard of trans fats? That's the whole problem with this hydrogenation. When you do a partial hydrogenation, you actually scramble some of the cis fats to trans fats. And even in trace quantities, that causes heart disease. If you want to get down a political rabbit hole, you can still label things as trans fat free when there's an appreciable amount of trans fats in there. You can imagine who lobbied hard for that. So there's a big push to try to get these trans fats and partially hydrogenated vegetables out of our diets, but it's a tricky thing to do. All right, so I did want to present a few other things. So let's take a look at this reaction. Let's predict what the product would look like if we do hydrogenation of this alkene. And pay attention to stereochemistry too, right? Right, the easy answer is we're just going to get rid of the double bond. And so what I see a lot of students do is they say, well, isn't this good enough? What do you think? What's the problem with showing it this way? We've got 2 stereocenters, right? They're undefined at this point. We want to define them. Do Do you think those methyl groups are both going to be wedges, dashes, or do you think it could be either a wedge or a dash? Do you think it matters? What do you think? Let's go back up and look. I said Syn addition of hydrogens, right? So the hydrogens would need to come off the same direction. So I'm going to go ahead and make both of those hydrogens wedges here to indicate Syn addition. What does that tell me about the methyl groups? They must be dashes, right? Do I have to worry about an enantiomer for this specific example? Why not? It's a meso compound. So in this case, we are only getting one product. It's a meso product, but there are stereocenters in a meso product, so we want to clearly identify them. All right. This catalyst system was the first one essentially used on a mass scale for these hydrogenations. These are called heterogeneous catalysts. Excuse me. And essentially what that means is that it doesn't dissolve. Like I said, the carbon is just charcoal. Charcoal is not going to dissolve. It's just going to sit there. It's going to be almost like a slurry. What you do is you put this in a pressurized vessel and you shake it. It's called a par shaker. And you pump in a bunch of hydrogen gas at high pressure and you just shake it for maybe half an hour and then release the gas and purify your alkane. What they found, though, is you can actually make some catalysts that dissolve. So let me show you this other catalyst system. Sorry, did you need to write that down? And in this catalyst system, you still need hydrogen gas, but what they do is they use a ruthenium atom as their chiral, or as their catalyst, along with a bunch of ligands. Does anybody remember what pH stands for? Phenyl, right? So it's a phosphorus with 3 phenyl groups coming off, and you've got 3 of those all attached to ruthenium, and you have 1 chlorine atom as well. This is called Wilkinson catalyst. This is called the Wilkinson catalyst for this specific reaction. And all it does is it helps things by dissolving. Again, ruthenium is really, really, really expensive, so we don't want to use very much of it. Having a catalytic system helps us out a lot. All right, let's predict the products we would get with this. It's the same idea, right? We're going to get to alkanes. This top methyl group is just hanging out there, right? If we think about, let's add a methyl group here for fun, because why not? If we think about the hydrogens, they're both going to add syn. So we could show both of them like that, which means this methyl group would be a dash. Is this going to be our only product? No. Our second product would be one that looks like this. Where both hydrogens are syn, but now they're both dashes, not both wedges. What's the relationship between these 2 products? They're diastereomers. Can we separate these out easily? Yeah, absolutely. They have very different physical properties. It's a lot harder to purify enantiomers, right? But diastereomers are easy to purify. All right, the main problem they had in the pharmaceutical industry was if you wanted to do this, you immediately lose half of your products, right? Because it's the wrong diastereomer. We have to be very careful about this. So what they found is that you can replace these with chiral ligands. So what they did was they just took these triphenyl phosphines, replaced them with chiral groups, and they're actually able to prefer hydrogenation on one side of the alkene and not the other side. So they're able to save 50% of their products from being wasted. So that was a big technological breakthrough. Really, the only way to prefer one stereoisomer over the other is to transfer chirality from your chiral catalyst to your final product. So it was a pretty big breakthrough in the late 50s. All right, good news. That's the last reaction for the chapter. What I like to do, though, is just a brief concept review to kind of pull everything back together. All right, so the first thing I like to review is the regiochemistry of a bunch of these. So let's say we've got an alkene like this, and we're adding a hydrogen in blue, and some other group, I'll call that A in red. If we think about Markovnikov addition, what group is going to end up where? Is the blue hydrogen going to end up in the middle or on the right? On the right. So Markovnikov addition says that our hydrogen is going to go to our less substituted carbon, and our main atom will go to the more substituted. So this is Markovnikov. Versus the other one, which we said is anti. All right. We saw a bunch of reactions that did Markovnikov addition. The first one we saw was pretty simple. It was with HBr, right? So if we did HBr, we could protonate that alkene, we get our more stable carbocation, and then bromine would add in. So in fact, I'm just going to color code this just to keep things simple. Right? So that was our hydrohalogenation. All right, the next one, if we think about it, is going to be our acid catalyst. Followed by water. Whoops, let me kind of color code this. Here we go. So when we did acid catalyzed hydration, right, we could add our alcohol to the more substituted side. So another way of writing this is just H plus or just H3O plus and water. It doesn't really matter to me. All right, and then the last one was HgOAC2. That was step one. And then step two, oops, sorry, I forgot water here. And the oxygen is going to get added to the more substituted side. What was the reducing agent that we needed in the next step? It was NaBH4, and the hydrogens from the borohydride actually added in anti-Markovnikov. So all three of these worked. All right, so now my question for you is, what if we want the bromine to go to the less substituted side? How do we do that? How do we get the anti-Markovnikov halogenation? We still want the bromine, though. The BH3-THF only works for alcohols. ROOR, right? So the next one we said is going to be HBr and ROOR. That does the anti-Markovnikov addition of bromine, right? And in this case, I'll just label this as the Br that's getting added to the more substituted, or less substituted side, excuse me. All right, the next one, I heard somebody say the BH3-THF. Followed by NaOH and H2O2. That also does anti-Markovnikov addition. Essentially, it's a complementary version of this one, right? So we've got options for both of those. All right, my question is, what was the purpose of this again? Avoid rearrangements. Do we have an anti-Markovnikov version? Yeah, essentially it's just the same thing, right? So it still would be that same reagent if we wanted to do an anti-Markovnikov addition of alcohols. All right, does that make sense? So sometimes I just like to take casual notes to remind us of anti-Markovnikov or Markovnikov. All right, next one is syn versus anti-addition. This is going to be addition of, I'll just call this X in red and Y in blue. All right, if we think about Syn addition, that means that they're both going to be on the same face, right? Meaning both wedges or both dashes. So I would maybe just say X and Y, and this would be Syn. And then we'll compare this to anti-addition, where we've got X and Y on different faces. We do have to worry about enantiomers with these, so I'm just going to write plus EN down here. But it is important to remember the stereochemistry that's going on, right? All right, so if we think about adding alcohols, how do we add two alcohols, both of which are syn? Does anybody remember how to do that? So what reagents do we need for syn addition of alcohols? So the MCPBA actually did the anti-diol. So let's actually write that down here. So you said MCPBA followed by some sort of acid and water, which I'll just call H3O+. That would do anti-addition of alcohols. So that would work for anti. What about syn? Osmium tetroxide. And then our reducing conditions usually are sodium bisulfite and water in the Klein textbook. Yeah.
On that first syn compound, isn't that a meso compound that's shown? But if it was a different compound, then it...
Yeah, so what Stacy's saying is, let's imagine the syn addition of alcohols here, just for fun, right? In this case, we wouldn't have an enantiomer because it would be a meso compound. So you're correct. In this specific example, if we did syn dihydroxylation, we get a meso compound. What about with the anti-addition of two alcohols? Would we have a meso compound? No, not anymore. So then we would have to worry about enantiomers. So yeah, good point. All right, so we can add two alcohols that way. All right, we also said another thing you could do was react this with KMnO4, sodium hydroxide, water, but you have to run this cold. Either situation will get you syn addition of alcohols. All right, the next one is kind of weird. This is hydroboration oxidation. And the way hydroboration oxidation works is you add a hydrogen and a OH group. Is it an OH? A OH group. Is it an? Is it an? I'm no English teacher, so we'll go with an here. All right, so we're going to add a hydrogen and an OH group that are going to be syn to one another. Will the OH group be Markovnikov or anti-Markovnikov? It's the one with boron, right? It would be anti-Markovnikov. Just like we said up here, it's this reaction, right? So that's hydroboration oxidation. But we do get Syn addition, and like we said, this would be BH3, THF, followed by sodium hydroxide and hydrogen peroxide. All right, the anti-addition, another one was bromination. Do you remember when we added Br2 to alkenes? The bromines added to opposite faces. So that'd be another example of anti-addition. You never get Syn addition of 2 bromines using Br2. So that's another option. What if we want to add 2 hydrogens? Will the 2 hydrogens go Syn or anti? Syn. So then we could say, sorry, I'll zoom out. Hydrogenation. That's where we use H2 and palladium on carbon. That always adds both hydrogens in a Syn orientation. So that works well. What if we have both bromine and water? So the Br2 and water, will that give us Syn or anti-addition? Anti, it'll actually follow the first initial step with the bromination reaction, which is a good clue that it's going to be anti-addition. And will the water add to the more or less substituted side? So the water, like we saw in the pod, any alcohol for that matter, will add to the more substituted side of the 3-membered ring with bromine in it. So make sure you practice that. All right, I know this can get really complicated. So I'll show you the thing that I like to do is at the end of each chapter, Klein has these reaction roadmaps where he says, all right, here's all the reactions I've thrown at you in this chapter. And he says, here's all the different transformations you can do with this one starting material. This is a lot to remember. But what I did in OneNote was I took that same map and I cut out all of the reagents. So what some students do is they just do a mental check and they say, can I remember what reagents I need for that transformation? Well, I'd look at it and I'd say, well, this looks like we're adding 2 alcohols. Are they Syn or anti? Anti. So what's a reagent we could do to add 2 alcohols in an anti configuration? Everyone looks so excited. So osmium tetroxide, would that one work? That does Syn diols, right? What do we need for anti-diols? MCPBA followed by acid and water. So up here on my cheat sheet, I'd say, whoop, that's not what I want. I'd say MCPBA followed by acid and water. And I would use this as a quick way of just refreshing myself. Do this over and over and over and over and over and over again until it becomes completely second nature to you. That's the best way to get good at this. I know it's not fun memorizing things, but the way I've described this to people is it's like learning a language. You have to know the vocab, but the problem-solving process of figuring out a mechanism or planning a synthesis, that's where the creative part comes out, and you can't memorize that creative part, but you do need to know the basic steps in order to get from point A to point B. So try to use this. The other thing I've mentioned is if you go on the website, on the class handouts tab, you might have noticed there's flashcards on the left-hand side. What some students in the past have done is they made flashcards on their own, just to self-study, or they've used mine and just cut them into strips. Whatever works for you. I have a preference for you making your own flashcards, just because when you write them down and make your own flashcards, you're actually studying without even realizing it. So just the process of making your own flashcards can help a lot. But try to keep detailed notes. So for example, if I were working on my flashcard for this reaction, I would make some notes. I would say it does anti-addition. And then what I might even do on the back of that note card is draw kind of a quick, simple mechanism going over the lecture notes. That way when I'm flipping through my flashcards, I can see the mechanism really quick too. But I do know this takes a lot of time. Try to do a little bit every night. If you, on Thursday night at 12:30 in the morning, are trying to cram this in, you will be mighty unhappy on Friday. So try to do a little bit every day between now and then. All right. Trying to think, are there any questions as far as the quiz goes? Yeah.
How long is the quiz?
So the quizzes will normally be about 30 minutes. I try to give enough time so that nobody feels super rushed, and then the last half will be new lecture material. The next chapter that we'll be getting into is alkynes. The alkyne chemistry is actually fairly similar to this. So the more effort you put into this chapter, the easier the next chapter will be. I will say often students look at this chapter and they're like, this is going to be a brutal year. I will say, in my opinion, this is one of the hardest chapters in the textbook. So just try to really dedicate yourself to understanding this material. This is going to be key to doing a lot of our synthesis problems down the road. Also, if you need to go back and review SN1, SN2, E1, E2, make sure you do that too, because none of that's going to go away either. So make sure you come tomorrow if you want to do review work. We can get groups together and we can do practice problems on the board.
Could you also